Let's check out the results to the spring lab and see what we can learn from it. So here are some sample results. So we have the data graph. You can see the table down here. And all I've done up here is given the equations for both of the best fit lines. So you can see the main difference between the two springs is their slopes are different. Looking at the intercepts, both of these intercepts are very small compared to the size of the spring force that we measured. Both of these are very close to zero. Visually, it looks like the intercept is zero. If you think about what we would expect the intercept to be here, if we have a stretch distance of zero, we would also expect the force needed to stretch a spring 0 meters would be 0 newtons. So basically saying like to not stretch the spring, it takes no force. So that makes sense. And so it's safe to say that these intercepts are actually zero. As I mentioned in class, some springs will have a positive intercept where with a stretch distance of zero, you'll have force of like 2 newtons or something. That tends to happen with stiffer springs that require a little bit of force just to get the coils to start to spread out in the first place. So if you see that, it doesn't mean you made an error in measurement or anything. It's just a characteristic of that particular spring. But in general, you would expect the intercept to be zero. So we can rewrite these equations like this. Now we can see the only difference is the slope. And so then we need to think about what this slope is actually telling us. This is where looking at the results of the entire class as a whole is better than just looking at yours individuals, because what this is measuring is the actual like stretchiness of the spring or the stiffness of the spring. And that's what that number represents. So a larger number means that it takes more force to stretch that spring the same amount. So if you kind of look at this graph, if I am stretching a spring with 5 newtons of force, the one with a steeper slope will not stretch as far with that 5 newtons of force as the one with a shallower slope. And that matches up with what we expect the slope to mean based on the units, that for every meter that this spring is stretched, it takes 80 newtons of force to stretch it that far. Whereas the smaller slope, the shallower slope, it only takes 47.4 newtons of force to stretch the spring with a displacement of 1 meter. The slope is measuring the stretchiness or the stiffness of the spring, with the bigger number, the steeper slope, being the stiffer spring. That has a very specific definition in physics, and we use the letter K to represent that number, and that is the spring constant. The spring constant, again, just is a property of each specific spring. Basically, how much force does it take it to stretch it a specific amount? This is the equation that shows up on the AP equation table. It has a negative K, and that is just because the displacement is opposite of the direction that the force is felt. So when the spring stretches down like we did, the force is up, and that's why that's a negative number there. So let's take an example and kind of see if you can see just visually which spring has a greater spring constant based on how it behaves.
All right, two springs, 2 cups, same amount of mass. Both cups have a 200-gram mass. That's enough. Put these on here, and these stretch between those two springs. Ta-da!